G'day guys, welcome back. So we're going to look at problem set 2, which mainly deals with inverse kinematics. However, first off, I'll just explain both forward and inverse kinematics. So, with a robot arm or something like that, some style of robot arm, you need to be able to describe whether where the tool point is in respect to the base frame. At any given point in time. Now, you could do that using transformation matrices and or using the DH parameters and working out the transformation matrices. And then for each configuration that the robot's in, you could then work out the transform, etc., etc., and relate what the origin would be back to what the origin of the tool point would be back to the base reference frame. However, inverse and forward kinematics do that. One, as inverse means, it's basically the inverse kinematics is the opposite of the forward kinematics. So what the forward kinematics does is it describes based on the joint angles and the prismatic values. So basically, how much a revolute joint has rotated and how much a prismatic joint has extended, where the tool point will be in a given workspace. So it will give you, based on your joint values, it will give you the X and Y, and potentially, if you're doing 3D robotics, the Z coordinate of where the tool tip is. And then inverse kinematics is the opposite of that. Given that you know where you want the tool tip to be, so you say you want it at a certain position in your workspace, so at some certain X, Y coordinate, if you're just doing 2D stuff, what do the joint values need to be for your robot configuration? So if it's a revolute, what do the two joint angles need to be? Or if it's a revolute prismatic, what does the first joint angle need to be, and what does the prismatic extension value need to be? Now, and so that's what we're going to look at today mainly. We're going to look at finding the inverse kinematics and how we can use this to move around our workspace and things like that. And if you actually are doing ENB339 Intro Robotics at QUT, you'll find this you might find this useful for the actual practical part of the course. Okay, so question 1. Find the inverse kinematics for the following revolute robot to give the angles for joints 1 and 2 for a given position of the tool point. So that's what I was explaining before. Part 2. If the robot initially starts at 300, 200, and needs to move to 0, 500, find the total number of degrees each joint has to move. Okay, so this is our robot down here. You notice that we're just, for this example, we're just going to be working in the 2D space. You can easily take this to be in the 3D space, but it can be a bit hard to visualize sometimes. So I've just kept it to 2D space. So you notice we have our first joint. So it's a revolute joint. Rotating, and this is our base reference frame, X0, Y0 for it, and the link joining it to joint number 2 is 300 mils long. Joint 2 again is a revolute joint, and it is 200 mils long. And so our tool tip is at the end, right at the end here, where my cursor is, where I've just put the blue box. So that's our tool tip. So we need to try and relate for question part 1, we need to relate, okay, this blue box, or the tool tip, back to the reference frame using inverse kinematics. So basically, what if we want this at, say, 0, 500, which is one of the values here, what would joint 1 and joint 2 need to be set at? The actual angles in order to reach that position. So we've got to find the inverse kinematics. Now, the best way to find inverse kinematics is draw a nice large diagram of it and smack on as many triangles are good things, angles that you can see, lengths that you could work out, or unknown and known angles. Okay, and obviously the very first thing sometimes people get confused is you throw down XC and YC, and these are coordinates that you actually know, because remember we're working out the joint angles based on a given position, so we know the position. Okay, so theta 1 and theta 2 are the main two variables that we're trying to work out here. So we're trying to work out theta 1 equals blah 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 blah, and theta 2 equals blah 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 blah, some formula or equation. Okay, So this is, I'll just walk through this one. So we've got x0, y0, which is our base reference frame. This black line represents link 1, which is 300 mils long, and that's theta 1 there, so that's the revolution. You then notice that I've drawn this dotted red line here. Now that dotted red line represents x1, because remember, if a coordinate system is attached to another coordinate system, so basically x1, or the first reference frame, or the first coordinate system, which would be used for theta 2 or joint 2, it basically, if the 0th reference frame rotates, then this one rotates with it. Okay, so this is actually x1 here, and so theta 2 rotates from x1 to wherever the link is, and so link 2 is 200 mils long, theta 2 there. You've then noticed I've also drawn these blue dashed lines. Okay, this one will be xc along the bottom, yc up top, and d1, okay, which we can find out just by doing Pythagoras' theorem. So d1 will be xc squared plus yc squared, square root of all that. Okay, you also notice on this part, these red dotted lines, I've drawn 200 cos theta 2 and 200 sine theta 2. So this red line would be 200 cos theta 2, 200 sine theta 2, so based on that angle there. Okay, the first thing that you should realize, especially when you have revolute, is you can actually get two sets of, or there's two potential configurations. So you could have, in the configuration I have now to reach this point, okay, and that's considered one position. This one would be, I believe it is called elbow down. Okay, you then can also have elbow up, so which would be it coming from the link 1 coming from the origin of your base reference frame up to here somewhere, and then link 2 going from there across to here. So you notice that you have 2 points, two configurations that could reach any point. Any point. There are some singularities, obviously, when the thing's fully extended. It can only have one configuration. So if the two links were in a straight line, that's its maximum reach, and so that creates a arc of singularities, basically. For a revolute prismatic, you'll actually find you don't get that problem. There is only one option for there's only one configuration for any given point. But for revolute, you just need to realize that there are two potential configurations. Okay, so the first one I'm going to start with, and I'm going to choose to start with finding theta 2. The reason for that is basically because depending what you choose, theta 2 will then depend on theta 1, and you'll see how that works a little bit later on. It's also kind of the easier one to start with, in my opinion, even though it may not seem like it. Okay, so theta 2. This whole angle here obviously is going to be 180 degrees. So theta 2 will be 180 degrees minus phi, which is that part there. We can then apply the cosine rule to find cos phi. So we've got this triangle here. If you go from link 1, link 2, and D1, we've got a triangle that we can use the cosine rule on to find phi. So D1 squared will equal 300 squared plus 200 squared minus 2 times 300 times 200 cos phi. Rearranging that for cos phi, you get 130,000 minus xc squared minus yc squared on 120,000. You can rearrange that if you wish. Okay, what we generally do is we then let D equal this business here, or let A equal whatever, this business here. Okay, as I've done there. You then, I'm not going to show the proof for it or anything like that, but phi will then be equal to A tan 2 of D. So this is the opposite over adjacent. So D plus or minus the square root of 1 minus D squared, where this thing up here is D, as I just explained before. Okay. I won't go into the proof of how this works. It just works. Okay. It has to do with the whole 1 is equal to cos squared theta plus sine squared theta. You can go look. I'm pretty sure you can go look into it if you wish. But there is how you go from using a cosine rule to finding phi. Now you could just go the inverse cos of this, but you generally want to use atan 2 in robotics because it gives you, and not just atan, but atan 2, because atan 2 actually gives you an angle between pi and negative pi, so the full 360s, a full circle, 360 degrees. The other arc trig functions, the inverse trig functions, they generally only find values between pi on 2 and negative pi on 2. They don't give you the full rotation. They just kind of then, if it was, say it was in quadrant 3, so it was greater than pi on 2, it would just then make it negative generally or something like that. So that's why we generally want to stick with atan 2, and that's why we do this. And just trust me that it works. Okay, the other thing you should notice is this plus or minus is consistent with that there's two solutions for theta 2. So you could do this and you'll do phi equals atan 2 d, use the positive term, so positive term is 1 minus d squared, square root of it. And then you could do, and that will give you one answer, using the negative will give you another answer, and that's, as we discussed before, you could have elbow up or elbow down, and so you can have two solutions for theta 2. So theta 2 will be equal to 180 degrees minus minus phi, which is this atan 2 d plus or minus the square root of 1 minus d squared, where d equals that. So that's theta 2. We then need to find theta 1. Okay, so up here, theta 1 will be equal to beta minus alpha. Now beta will simply be, looking at this, it just creates a triangle using xc, yc, and d1. So we can apply atan 2 to xc and yc to give us beta. So beta will be equal to atan 2 xc yc. You then know, and then alpha. Okay, we can also then create a triangle if we follow the link 1 and the red dotted lines with d1. We find we have another triangle which we can then use to find alpha. So alpha will be atan 2 of 300 plus 200 cos theta 2 and 200 sine theta 2. So alpha will be atan 2, 300 plus 200 cos theta 2. So that's the